All right. Um, so I want to welcome you to this lecture series. It's the first, as the first, and we're going to be going over lots of physics principles from a conceptual basis. From a conceptual basis. So we're going to be looking at concept first approach. Um, so we're just going to run over, in each of the series, we're going to run over different topics in physics and look at the concepts just so that you form sort of like a mental framework of um, how these physical principles interact in the real world. And with that, you'll be able to tackle any problem, any physics problem you come in contact with. You'll be able to make better sense of the world around you. All right? So let's get started. So we'll be looking at motion, in particular, motion. Um, so just to give us a bit of history, a bit of context to what we're doing here. So what we today know as, and I think you're going to appreciate this, what you today know as Newton's first law, Newton's first law of Newton's first law of motion. So what you today know as Newton's first law of motion. What you today know as Newton's first law of motion took about 2000 years. Took about 2000 years. The breaking up of the then church, um, the burning of a scientist on a stake, and numerous open experiments for us to arrive at Newton's first law of motion. And at the end of today's class, today's lecture, you're going to appreciate what I mean by, all this history. Okay. So, thereabouts in, you know, the ancient times, Aristotle, very important in physics history. Aristotle, many of you know Aristotle as um, an ancient philosopher, historian and all. But Aristotle was the first to you know give thoughts to motion. Okay, he was the first to give thoughts to motion and the concept of how moving objects interact or things around us move. And so, one of the beliefs of Aristotle divided motion into two. He classified it into, maybe I should just begin to write them down here. He divided them into two. He called one natural motion, and he referred to the second as violent motion. Okay. Or he said that natural motion is the kind of motion that occurs naturally, in the sense that objects will strive objects will strive to attain their normal place according to their nature. And this nature, he said, is made up of one or more of these four elements. Okay? One or more of these four elements. And the four elements, as you know, earth, fire, air, water. Yes, you guessed it right. Avatar. Okay, so Aristotle said natural motion occurs when an object strives to attain its normal position based on its nature. So, for instance, a lump of clay will strive to come back to the earth if not held up by anything. So, it always strives to come back to the earth. Smoke, if not enclosed, if not impeded, will strive to get into the air. Okay? Leaf, for instance, will strive, although he said leaf, both made up of um, earth and air, will strive to come to the ground, to earth, because it has more of earth composed in it, much more than it has air in it. So are you getting the picture now? So objects will strive to get to their most natural states, of which he believed this most natural state is that of rest. Okay? Um, so these four elements were made what is what make up natural states of elements. So Aristotle was also of the opinion that objects, heavier objects, would strive harder. Okay? So heavier objects will strive, heavier objects will strive harder. Heavier objects will strive harder. So that means that what Aristotle was saying is that a stone is going to fall faster than a feather because it has more of earth in it as compared to a feather or to a leaf. So it's going to fall faster. In other words, he was saying the speed at which objects fall to the ground is proportional to their weight. Okay? So you begin to see the first frameworks of scientific thinking, as it were. All right. So these were some of his postulations, and there are more. There are more. So Aristotle also believed that Aristotle also believed that um, there was a third kind of motion. For this, he called quintessence. Quintessence. And this one was reserved for celestial bodies, right? So, celestial bodies, the earth, the sun, the moon, other planets, the stars. So, so Aristotle believed that there were two different kinds of laws for both the heavenly bodies and the earth, bodies on the earth. So he believed that this one had to do with motion on the earth, and then this one had to do with heavenly bodies, right? So two different laws for two different kind of bodies. And what did he describe as quintessence or quintessential motion? These are these are movements that have to do in circles. So, for instance, he observed that the sun moved or revolved around the earth. So, um, let's say this is the earth. Let's say this is the earth, and this is the sun. Okay, earth, sun. So this rotational motion here he described as quintessence. So the movement of celestial bodies, he said or he postulated that celestial bodies move in a perfect state, in a perfect circular motion, continuously, unending. All right. So he had two different laws for the heavenly motion and that of the earth. So just to summarize what Aristotle came up with or what he thought, mm, number one, Aristotle believed that motion was divided into two: natural and violent. Number two, that the natural motion, I'm going to explain violence in a bit, but first of all, let's deal with natural motion. So that first of natural motion had to do with objects striving to get to their most natural state, their place of rest. And these natural states, this nature had to do with the four elements, okay? So depending on what you are made up of, depending on what comprise you, you're going to strive to get to that place, okay? So a stone, for instance, will strive to get to the earth. A feather will strive to get to the earth, although it's made up partly of wind and of earth. It's going to strive to still get to the earth. A um, a smoke, for instance, will strive to get to the atmosphere. Okay, so he said, earth, fire, air, and water. Number three, objects will fall in speeds directly proportional to their weight. Okay, so objects will fall at speed directly proportional to their weights. So heavier objects, they're going to fall faster. Lighter objects will fall slower. We know this today to be false, but then this is what we had. And we have to appreciate this because it began to form the very first foundations of what we today know as scientific thinking. All right. And another thing he observed, and this is where, okay, I've also mentioned quintessence as motion for celestial bodies. Quintessence, right? Motion for celestial bodies, in the sense that they move in a perfect circle, unending, right? Then this is where the Aristotle claim or postulations, started becoming a little bit difficult and started breaking. Things were not adding up, all right? Because when he began to describe violent motion, so violent motion he observed or he said were forceful motions. So any motion that is not natural, any force that comes from the external is referred to as violent motion. So for instance, the wind blowing against the sail of a ship, the um, pushing and pulling of objects. So when you push an object or when you pull, that's violent motion. So that's forces outside or external to the object. That's violent motion. Forces external to the object. That's violent motion. All right. And so questions began to be asked. Questions like, um, when you pull a, so look at this. When you pull a bow and an arrow, right? So you have to forgive my drawing. Oh dear. So let's call this the bow, okay? Let's call this the bow. And you have string here. Let's say you have an arrow. Okay. So you have an arrow here. Okay. So at the moment you release this arrow, okay, At the moment you release this arrow this way, okay? At the moment you release this arrow this way, for about, you know, less than a second, less than 1 second, this string here will still hold on to the base of this arrow. But as soon as it leaves this arrow, and the arrow keeps on going forward this way, right? What then is responsible for the movement of that arrow in that direction? Okay? What's responsible for the movement of that arrow in that direction? Aristotle believed that there was no vacuum, and for violent motion, there was always an external force to push it. And so, what he explained for this one, for this particular, um, idea of the bow and the string, he says it's like the arrow, is as it parts the wind in front of it, it forces the wind behind it and closes up that gap, and that continues to push the arrow forward. Just the same way you would press towards the end of a bar soap in a bathtub, right? And the soap is going to spring forward, you know. So that's what his explanation. That as the arrow begins to pierce through the air, the wind resulting from that movement rushes to the back to fill up that space, and then the arrow keeps going forward. You know, that began to be a little bit difficult to explain, and that's where things were not just adding up, but that was the belief then, because at that time it was inconceivable for there to be any force greater than, or any force um, capable of moving the earth. And so it was only reasonable and logical to come to the conclusion that everything revolved around the earth. So, um, suffice to say that this belief was held for about 2,000 years. You know, about 2,000 years. Now, note that Aristotle lived before Christ. He lived about 300 thereabout BC. And so his postulations formed the scientific world, the scientific idea all throughout this season for about 2,000 years. And so this brings us to the next person we have in our timeline, and his name is Copernicus. Copernicus. I hope I get the spelling right. Copernicus. Yes. So Copernicus came up with the postulation of the moving earth. He came up with the postulation of the moving earth. So, Copernicus began to question some of all these things, and he said the only logical explanation to some of these things is, or what he understood, he was like, the only way for us to explain the movements of the sun, the moon, and other planets was that the earth had to be the one moving around the sun, you know. But up to this time, he didn't have any proof or scientific backings, because some of the claims and postulations of Aristotle were not adding up. So he began to question. And so he first came up with the idea of the moving earth. And he said, what if the sun is not revolving around the earth, but rather it was the other way around? Now, this may sound easy and you know, easy and quite within your mental grasp. But as at then, it was a very big statement to make, because you are not only questioning the authority of Aristotle, they are questioning the church itself, the then church. As at that moment, the ideas of Aristotle had been enshrined into the doctrine of the church and the identity of the church. So Aristotle held a lot of influence even after his death. And so nobody was willing to go against um, the idea of the day. And so Copernicus, even after doing numerous research, conducting not necessarily experiments, but writings, lots of findings and all about this, he never published it up until the day of his death in 1943, in 1543, sorry, in 1543. So eventually, after his friends pressured him, he sent out his findings for publication, and it arrived at his deathbed, the very day he died. The first copy of his exposition reached him on the day he died, May 24, 1543. And so, well, he didn't live to see what what will become of his findings. But history is there of what happened, based on that publication and all. The it was fought, and for better or for worse, this new idea was overturned. This new idea was to overturn their conception of the cosmos, but they didn't embrace it as at the time. Okay, so this is, this is the much you can say about Copernicus, because he was actually the first to recorded in history to begin to challenge the ideas of that began to challenge the ideas of Aristotle, at that time. And he only published his paper in 1543, the day he died, unfortunately. But then this brings us to the third person, because exactly 21 years after, Galileo Galilei was born. And yeah, most of you know about his famous Leaning Tower of Pisa experiment. And so Galileo Galilei, although was not the first to dispute Aristotle's claims, he was the first to begin to experiment on them and, you know, release findings on them. So Galileo Galilei gathered the first idea he disputed was the idea of um, heavier objects will fall faster. And so, to dispute that, he had to carry out experiments. One of them is the famous falling balls from the Leaning Tower of Pisa. And so, Galileo showed that balls, in fact, or objects, in fact, do not fall at speeds proportional to their weights, but that they fall at the same speed if there is no resistance, be it air resistance or friction or whatever. And so he first of all showed that both big, so he used balls, right? So small balls, small and big balls fall at the same time. And so with this, it was shown that objects and facts, the weight of objects in fact is not responsible for how fast they fall. So speed of fall is not equal to the weight of objects. It's not directly proportional to the weight of the objects. So he showed it. And he went on to conduct numerous experiments like that of the inclined plane. So another thing Galileo observed was if you put a ball at this point, all right, you put a ball at this point and put a ball at this point, Galileo observed that the ball, let's say these two angles here and here are the same. Galileo observed that the ball will fall through the inclined plane, all right? The ball will fall through the inclined plane. Let me use the ball will fall through the inclined plane and rise to about the same height of its original position. So he also conducted similar experiments, but this time he reduced the angle of inclination, you know, slightly. But this time he reduced the angle of inclination slightly. So instead of making it steep, he reduced it this way. All right. So if the ball starts at this position, how far up will it go? And he discovered that it will go even further. Okay? It will go even further. So this is initial start position, and he observed that it would surpass the initial start position. So what did that tell him? He began to show that, okay, so we make if we make this if we make if we make this other inclined plane here entirely flat, what happens? So it simply means that the ball will never get to this original start position, meaning it would keep on moving indefinitely. So in the absence of any opposing force, this ball, the tendency is that this ball will continue to move. All right. And so it was this idea, this observable future, this predictable behavior that this ball, this object will continue to move continuously. He described as inertia. Okay? He described as inertia. So this was where the first idea of inertia came about. Okay? This was where the idea of inertia came about. So Galileo's concept of inertia discredited the Aristotelian theory of motion. Aristotle did not recognize the idea of inertia because he failed to imagine what motion would be like without friction. And now, just think if you think that it was just as easy, well, when Galileo, conducted lots of experiments and also reported dark spots, he found dark spots in the sun. Now, Note that it was Galileo Galilei that invented the first, not the first telescope, but the first to be used for astronomical observations. And so this was in 1609, thereabouts. But 9 years before, Giordano Bruno was burnt on a stake. Giordano Bruno was burnt on a stake because he held firm to his belief that Copernicus' model of the solar system was correct, as opposed to Aristotle's model or Aristotle's belief. So he was burnt, you know. So Galileo Galilei, upon hearing that he had to retract some of his discoveries, especially of that of the sun, because they believe that the sun was perfect, spotless, it was without blemish, and God made it that way. And so any blemish in the moon had to be because the moon was closer to the earth. And so the corrupt nature of man has affected the moon, and so that's why the moon had some curves and some blemish. It was not perfect, but that the sun was perfect. And so anybody that would oppose that is seen as blasphemous. And so Giordano Bruno was burnt on a stake. So Galileo, upon to avoid the same fate, he had to recant some of his discoveries. Okay, so but nevertheless, he published others, and it was this his observations and numerous experiments looking at the sun that got him blind at the age of 74. You know, got him blind at the age of 74, and then he died, some years afterwards. But it was from Galileo Galilei that things began to make sense. And this was in the 17th century, right? And I want you to now sort of draw back, and Aristotle existed 300 BC thereabouts. And the first time we are coming about the idea of inertia was in the 17th century. So this is over 2,000 years thereabouts that science, experienced a pause. And so it was Aristotle's idea that a moving object must be propelled by a steady force. It was completely overturned by Galileo, who stated that in the absence of a force, a moving object will continue moving. Okay? So the tendency of things to resist changes in motion was what Galileo called inertia. And so Newton refined Galileo's idea and made it his first law, appropriately called the law of inertia. And so that's what we now know today as the famous Newton's first law of motion, that states that every object will continue, every object will continue in a state of rest, will continue in a state of rest or uniform speed in a straight line, or uniform speed in a straight line, unless acted on in a straight line, unless acted on by a force, ideally a non-zero net force. All right, so there you have it. This is how we arrived at Newton's first law of motion. And so we're going to continue on this series in another video. We're going to pick it up from here, but this is just to give you an idea of, how we got to this point. and that you should strive, continue to fight for your ideas because, you know, we'll somehow appreciate these things better when we know the history of things. To know that persons actually lost their life, lost their freedom. I failed to mention that Galileo Galilei was imprisoned at some point, for his ideas. So we should appreciate science and fight to make it better. All right. I was reading through a book and I saw that was statistical mechanics. That the person who started studying it died, while studying it, and now it's our turn to study it. Should we still continue? So imagine you are being asked that question. So the person working on this topic started and died on it. It killed him, and so now it's your turn to study it. Will you go ahead and study it? So that is about how we came about motion, or what we have today as the first law of Newton's first law of motion. And you can see that all the way from about 300 BC, we came to the first law of motion in about 16